So I guess I wanted to, before I get started, just thank Dan and Asu and all the people who were involved in making this building awesome. Thank you. A reality. I can't imagine how much work it took to get to this point. So it's exciting to be in the space itself. So I wanted to first call out the PhD students who are involved in this work. So it's Emma Dotterman from UC Berkeley, and then Alexandra Hensinger and Matt Hong from MIT. What I see as one of the grand challenges of the next many years is figuring out how we can get the benefits of cloud computing. So think about Google Calendar or Gmail or Google Search or any of the services that you use online today without having to pay the cost of data breaches, mass surveillance, abuse of user data, people reselling your data and using it in ways that you didn't expect. And I think we really don't know how to solve this problem yet. So just to situate this in the context of Vinod's talk, I see this kind of privacy-preserving world as some planet far away where we can use Gmail without giving Google any of our data. And we're down here on Earth. And traditional cryptography was extremely useful, is still extremely useful, as Vinod said, but it's not really powerful enough to get us there. And it's only been in the last something like 15 years, as Vinod was saying, that we've developed extremely powerful tools for solving these kind of privacy problems. So now it seems like it's possible. But still, we haven't quite gotten there. And I think the reason we haven't quite gotten there is we haven't figured out how to use these tools super effectively. And if you don't know how to use them effectively to solve these privacy problems, you don't get very far at all. So what I am going to talk about today is one attempt to kind of use these really modern cryptographic tools to solve one privacy problem that's at least a piece of the bigger issue. And I hope to convince you that we at least can be on a trajectory towards this much more privacy-friendly world. So I should say, by the way, it's a small enough audience that you should feel free to interrupt me with questions if you have any as you go. Great. So I'm going to talk about private web search and is a case study, essentially. And the reason I want to talk about web search is that the web search queries that you make reveal some of the most sensitive information about you. So they reveal your health conditions, your financial status, your religious beliefs, citizenship status, relationship issues, all sorts of things. You can imagine, I mean, if you think about what you type into Google, it's quite revealing. So the privacy problem there is that when you search for something on Google, for example, search for a knee problem, you have to send your search query to the search engine for the search engine to be able to answer it. So they have to look at your query, often they'll log it, and then send the relevant URLs back to you. The problem with that is that if an attacker is able to breach the search engine, or the search engine decides to resell your data, or a government comes asking for it, all of your sensitive data can flow out into the world in a way that you didn't expect. So the goal of this system that I'm going to describe to you is to allow you or some client to search the web without having to reveal your search query to the search engine. And we're going to use the tools, the kind of tools that Vinod was just discussing. So in the end, why this is useful is that if the search engine never actually sees your search query in the clear, it can't leak it to anyone. So even if the search engine gets breached or someone comes and steals its servers, it doesn't have any of your sensitive data to reveal. So that's the goal of this system. And there's a bunch of things it doesn't do. For example, we're not going to try to hide when you're making search queries, or we're not going to try to guarantee that you get the right answers to your search results. All we're focusing on for now is privacy, which is already, in some sense, hard enough. So there's essentially two types of search engines that you can use today. So one are the commercial ones that work at very large scale, so as you know, but always have to see your query at some point to answer it. So even if you're using DuckDuckGo, DuckDuckGo is going to see your query at some point. And that I assert as a privacy risk. The second type of system are sort of researchy academic systems that do in fact hide your query in the way I was describing, but that don't scale up to very large data sets. So the biggest system, before the one I'll tell you about today, could search over Wikipedia, something like 5 million articles. And the main challenge there is that the sort of text search algorithms that we have tend to work make many random accesses to a very large data structure, whereas the fully homomorphic encryption schemes that we use, the most efficient ones, tend to require your computation to be represented as a Boolean circuit. And that mismatch causes, basically you have to compile your search algorithm into a Boolean circuit, which blows it up to a size that's like totally impractical to run on a computer, or on a computer, much less under FHE, fully homomorphic encryption. So this search engine that we built, we call it Tiptoe, and it provides this very strong privacy property. So the server only sees an encryption of your search query, and yet we can search over kind of hundreds of millions of web pages with a few seconds of latency. And the communication cost is bigger than with Google. It's sort of tens of megabytes. But still, the fact that this is possible, at least to me, suggests that we're on the track to scaling this up and making it a reality. The other nice thing, for reasons I'll describe, it can actually support image search or code search or audio search, any type of search that you want. The downside, of course, there's always a downside, is that the search quality, as you'll see, is not going to be Google search quality, but it's usable still. So I'll explain more about why that happens at the end. So okay, I've tried to explain to you why this problem is important, or at least important to me. I want to spend a little bit of time explaining to you at a high-ish level how the system actually works. So forgive me, I think some of this might get a little too deep, but if I lose you, I think I'll catch you in 3 slides or something. So the architecture of this new search engine looks as follows. So we have this, we basically take a crawl of the web on the upper right, and we index it. So we run a bunch of computation offline to generate some data structures. And those data structures are used by 2 different services, client-facing services. The first service takes as input an encryption using a certain type of homomorphic encryption scheme, a function of the client's query, and under encryption, maps it to a set of scores, 1 score for each document. So for example, here, document 92 is the document that's most relevant to the client's query. Then in the second step, the client takes its document ID, sends it under encryption to this URL service, and maps it under encryption to a URL. There's sort of 2 steps here. The second step is actually more or less standard. You can solve this with off-the-shelf cryptographic protocols. We have our own version of this that's pretty fast, but I'm not really going to talk about the second part. The first part is actually the challenge. So how do you take an encryption of a query, like knee problem, and turn it into an encryption of document scores, like some values that tell you which of the URLs is most relevant to you? So we have 2 basic design ideas that make this possible. And I think at a high level, you can think about it as designing a new kind of search algorithm that's friendly for use with homomorphic encryption schemes. So trying to kind of figure out how to design a search algorithm that's good enough and yet can kind of play nicely with the encryption schemes that we have. The first design idea is to reduce the problem of free text search, like searching the web, to the problem of nearest neighbor search in a vector space. And the key tool for that is something I'll describe on the next slide called the semantic embedding, which is a recent, it's a very old idea, but the quality of these things has gotten much better in the last few years as a result of a bunch of machine learning work. The second contribution, or the second idea, is a super fast protocol for private nearest neighbor search. And the ideas there, we use clustering in the first step, and then some very fast homomorphic encryption scheme in the second step. And I should say, the kind of homomorphic encryption we're using is based on the learning with errors problem, as Vinod just discussed, but we're not going to need a fully homomorphic encryption scheme. We'll only need an encryption scheme that supports evaluating linear functions under encryption. And that's one of the ways that we get this to go fast. So okay, let me tell you about the first step. So the idea is to reduce the problem of private text search to the problem of private nearest neighbor search. And the way we do that is by representing each document in our corpus, so think about each web page, as a vector, and a pretty small vector, so like 192 floating point numbers is what you should think about. So we have all these documents on the right. Think of the pictures as documents, and we're going to map them into vectors in this vector space. And the key property of this mapping is that when two documents are close in content and kind of they're both talking about apples, say, they get mapped to vectors that are very close by in vector space. And the way we measure closeness here is their inner product or their dot product is large. And if you take a document that's not related to apples, it's going to map to somewhere far away from the apples in vector space. So that's a semantic embedding. It's not obvious that you can actually construct such a thing, but it turns out now online you can download one for free, and they're surprisingly good at doing this. So the way this helps us with search is that the client now can take its search query, it can locally embed it into a vector without talking to any server, just using a embedding function that's stored on its device. And now the client, all the client needs to do is find the sort of the names of the vectors that are close by to it in vector space. So for example, here these vectors would be the ones that are most relevant to the client's query. So now the task is how do you find these vectors without revealing anything to the server. So just to kind of emphasize why these embeddings are super useful, they both reduce this messy problem of text search to nearest neighbor search, which is a very clean problem. Another nice feature is that you can optimize the embeddings independently of the crypto. So as the machine learning people get better at doing this, the search algorithm that we build gets better. And you can embed almost anything into a vector. So images, video, code. This is a very general technique. So this private search engine is actually pretty general too. And the last thing is embedding has no effect on privacy. So the privacy is independent of how good the embedding is. The embedding just tells you how good the search results are going to be. So okay, that's the first idea. Any questions? Questions so far? Yeah. We get them, so I'll put the names up of the particular embeddings that we use, but they're just online on Hugging Face if you know it. Yeah, good, thanks. Any other questions? Okay. Yes, we use neural net embeddings. Yeah. So I guess I'll say at the end why we do instead of the other approaches that we could use. Yeah, Arvind.
Can you say a word about what is the difference between preserving this nearest neighbor property on encrypted data versus non-encrypted data?
So we haven't used any encryption yet. So this is all just on non-encrypted data. The encryption only comes in when we try to do the nearest neighbor search. So basically, all we've done now is we've mapped all the documents into vectors, we've mapped the query into vectors, and the nearest neighbor, the encryption comes in to figure out like how does the client fetch the nearest neighbors without revealing its query to the server. Yeah, awesome.
The point is that the encryption is the same answer.
Yeah.
Does it have anything to do with what Proton had done a long time ago, nearest neighbor hashing or something?
So there's many ways to do nearest neighbor search. They, for a bunch of reasons, the way that you do nearest neighbor search on plain text data, on unencrypted data, is totally different than the way we're going to do nearest neighbor search. And the reason for that is that the locality sensitive hashing, these kind of nearest neighbor search techniques, are kind of fast on a RAM machine when you can make random access to a data structure, whereas fully homomorphic encryption, at least the more practical versions of it, don't allow you. They don't support random access. They support Boolean circuits. So that's kind of where the mismatch is. Yeah, excellent. Okay, cool. So now I'm going to tell you about how we do this private nearest neighbor search under encryption. There's two steps to this. The first step is the client's going to figure out which vectors, what neighborhood it wants to look in. And the second step is it's going to find which document in that neighborhood is most relevant to its query. So we have these embeddings, and what the server is going to do in a pre-processing step, or the search engine, is it's going to group these vectors into clusters. So there might be a cluster about apples, there might be a cluster about knees, there might be a cluster about universities, and so on. And it's going to send the centers of these clusters, the centroids, to the client, and the client will cache them. And it turns out this doesn't actually take a ton of space. So when the client now wants to make a query, it can embed its query into a vector. And using this local cache of cluster centers, it can figure out which cluster is most relevant to its query. So the client has not talked to the server yet. This is all just local stuff. So the tricky part now is how does the client figure out which of these which of these documents, say in this, so the client's query here is closest to cluster 2. Which of these URLs in cluster 2 is most relevant to its query? So the goal essentially is for the client to fetch the inner product scores, the dot products of its query vector with all of the document vectors in cluster 2. And the way we do that is with a certain type of homomorphic encryption. So what we have, the type of encryption scheme we use is one that allows multiplying an encrypted vector by a public matrix under encryption. So if you have some vector encrypted, you have a public matrix, you can kind of, without knowing the decryption key, map these two things into an encryption of the matrix times the vector. That's the type of homomorphic encryption we're going to use. So how do we use that type of homomorphic encryption scheme to solve this nearest neighbor problem? The way we do it is we arrange all of the vectors in this document corpus into a gigantic matrix, where each column of this matrix contains all the vectors in a cluster. So these are all the embedding vectors for the documents in cluster 2. And then we have the client prepare an encrypted vector that has zeros everywhere, except with its query embedding stuck in position 2, if it wants to search over cluster 2. And I should say the entries of all these things are actually vectors, but I'm drawing them as scalars just for simplicity. So the client sends this encrypted vector to the server. This is all the client ever sends to the server. So the server never sees the query vector, never sees which cluster the client's interested in, doesn't see, all it sees is ciphertext. But if you look at what happens when you take this matrix vector product, what you get back is the inner product of all of these embedding vectors in cluster 2 with the client's query vector. So what comes back to the client is a set of encrypted document scores, one for each document in cluster 2. And then the client can just decrypt this vector, look for the largest value in it, and realize, okay, document 3 here is the one that's most relevant to my query. So this is a way that under encryption, using a certain type of homomorphic encryption scheme, the client can figure out which document is most relevant. Question? Yeah. Yeah, so it's not billion by billion, but I think we have in our system something like 50,000 clusters. And each cluster is 10,000 documents, something like this. Yeah. So it's a big matrix, and it's stored. We store it, as I'll show, across many machines. So yeah, very big matrix vector product. Any other questions? Yeah. Perturbing the query vector with noise. Whoop. Instead of encrypting it, you're saying? Yeah. So you could do that. The problem is, even if you perturb the query vector with some noise, it already reveals a lot of information. So for example, if your query is about apples, and you perturb the apple vector, your query vector, it's still going to lie in a subset of a piece of the vector space that's about apples.
That is sort of the correctness property in a sense, right?
Exactly. Yeah. So the properties of the embeddings essentially mean that if you perturb these vectors a little bit, they don't change the sort of semantics of the embedding. So put it a different way, it wouldn't be secure. That would be the issue. Yeah. But good question. Yeah.
So the number of different encoded vectors that can go as a prompt or the query in the first place are just equal to the number of clusters, right?
So the number, you're saying, what are the number of possibilities for this value Q?
Is it just the same of the number of clusters?
So you're saying the dimension of this vector? This vector? This vector is as long as the number of clusters, so there's one entry here for each cluster, times the dimension of this query vector, which is like 192. So the reason for that is that so the number of rows in this matrix is like the number of documents in each cluster, and the number of columns is like the number of clusters.
Oh, so it's not just the one, it's
Yeah. Sorry, I didn't write them as vectors here, but they are vectors. Yeah, good question. Oh, excellent. We have one more. Yeah?
About like an edge case where the best document is actually not in the documents cluster, but in neighboring cluster.
Yeah. This is an excellent question. So what if, so just to make sure I understand it, so what if you think, I guess going back to this picture, oh, I can only reverse very slowly. Okay, so what if this, you think that the best document's in cluster 2, but actually there's some document over here in cluster 3 that's more relevant to your query? You won't find it. And that's essentially why the search quality of the system suffers, because it's giving you kind of a very fuzzy, very approximate nearest neighbor search, whereas if we were able to do an exact nearest neighbor search, we would actually do much better in terms of search quality. So I'm gonna go on for a bit just so I don't run out of time, but at the end, if we have time, I'll take one more. Okay, so I guess the thing to point out is that the communication cost here is much less than the number of documents in the corpus. So it's like square root of the number of documents, which can be like megabytes instead of gigabytes, terabytes of data. Okay, so those are the two ideas. The last thing I wanted to mention is, so we have this fast encryption scheme. This is joint work with students Matthew Hong and Sarah Michael-John and Alexandra Hensinger, whose name I should have put here, and also with Vinod. Yeah?
Before you move on, I'm just curious about a concern that a search engine provider might have of not wanting clients to learn too much of their search index. That force client-side search, how does that concern play out?
So the concern is that the search engine might want to hide its search index. And in this system, just to make clear, the client is learning a lot of stuff, right? It's learning the relevance scores of all of the documents in this cluster. And that might leak some information about the search index that the server doesn't want to reveal.
But also there must have been some pre-computed information about all the clusters that you moved to the client.
That's right. Yeah, the centers of all those clusters and so on. So the cluster centers I actually don't worry about too much, because you can compute those, just take a list of common topics, embed the topics. They're not terribly sensitive. I think this sort of leakage is much harder to defend against. And we haven't thought about it. I mean, I think that, I guess I'm always thinking about the client privacy side of things. I think when you care about the server privacy side of things, things get more complicated. I don't know, Vinod, do you have a? Yeah. Okay. Cool. Okay. So so this is to just give you a sense of how fast this type of homomorphic encryption can be. And this is the result, again, of work with many people at MIT. Sort of for each byte of the matrix, when you're doing this encrypted matrix vector product, all it takes computationally is like 2 32-bit word operations per byte. So it's this is like 10,000 times faster than maybe even more than that, more like 100,000 times faster than what people were doing, say, 15 years ago. So the performance has gotten really good, which makes some of these things possible. So just to recap, what the client does is it embeds its query into a vector, finds the nearest cluster, and then figures out the scores of all the documents in its cluster, and then can map that document ID to a URL, all under encryption. So okay, that's how the system works. The questions give me confidence that I didn't totally botch the description. And now I want to tell you a little bit about how it actually works in practice. So the students implemented all of this stuff, and these are the two embeddings that we use. They're just off-the-shelf, pre-trained ones. And it's some thousands of lines of code. And when we implement it, sort of to your question over there, the matrix is gigantic, so we split it across roughly 40 machines. And the URL service runs on a smaller number of machines. And the numbers I'm going to present to you are kind of over a simulated wide area network. So how did it do? I think this, for me, is kind of showing you the difference between, in some sense, the difference between a bicycle and a space shuttle in terms of performance. So we can scale up, 100 times larger data sets, much bigger search index, and while reducing the computational cost by like 6,000x or something. So this modern crypto is really helping us get performance here. And the communication cost and the dollar costs have also fallen. Yeah?
Just curious why you chose many machines with 4 cores each instead of fewer machines with 4 cores.
Yeah, basically, memory bandwidth is the limiting factor here. The computation doesn't matter much. So by choosing a larger number of smaller machines, we could have the cheapest experiments with the largest memory bandwidth. Yeah, great question. Yeah? Yeah, so we do both image search and text search. We evaluate it on. Yep. All right. Okay, yeah, so the reason for this, someone was asking, did we use neural net embeddings or not? So these modern embeddings are like 100x smaller than what you would get if you used a kind of a 1960s type semantic embedding. And that gives a big speed up. The crypto optimizations that we have give another 10x speed up. And then the clustering optimization that prior systems didn't use gives another big reduction in the communication cost. So all those things together is where these savings come from. So then from client perspective, I don't need to go in depth into these numbers. I think the important thing is that for sort of hundreds of millions of documents, the queries take a few seconds and some tens of megabytes of communication. So this is like, you know, to me, went from being science fiction to being something that's, okay, it's still slow, but it's not, it doesn't seem impossible anymore to me. And the catch that someone was alluding to before is that the search quality suffers a bit. So if you look at the best non-private search engines, they're doing on this standard benchmark, they're doing much better than we are. So we're down here. These are, so this is a state-of-the-art search engine. These are two kind of classic 1970s type information retrieval algorithms. So if you think about in terms of the ranking, if you have a search for something and you look at the top 100 results, the non-private things will rank the true best result at like position number 2 and will be down at position number 7. So it gives you a sense of what the quality looks like. I guess I thought I'd show just some example queries to give you a sense of what also goes wrong. So this is, if you search for conceptual things, like how long before eagles get feathers, you do get a page back about eagles. And in fact, this is a fledgling eagle that's getting feathers after 10 weeks. So sometimes it works. Same with things like the definitions, like the meaning of haploid cell, you'll get the Britannica article back about haploid cells. Where it really doesn't work is for exact string search. So if you search for 77 Mass Ave, you get a page back about 898 Mass Ave, which is close. Like you can sort of see what was going on, but no cigar. And the reason for that is that these semantic embeddings, they're really not set up to do exact string search, where algorithms like what Google uses are doing a combination of things, embeddings plus other algorithms that are better at string search. Yeah.
This sort of thing is like keyword search in a sense, right?
Yeah. Yeah. Yeah, so the question is, this is almost like a hash table lookup, keyword search. So why can we combine these things? And I think the answer is absolutely yes. I think my guess, I don't know how Google works, my guess is that it takes your query and runs multiple search backends on it. So addresses, phone numbers, keywords, and we could totally do that. We haven't tried to see how well it would work, but I can totally believe that, for example, addresses, if we special case that, if we special case phone number, we special case names, the search quality would get much, much better. Yeah, excellent. So I'm optimistic, right? There's a lot of room to improve. So okay, just to summarize this part, or this case study, I think you can get very good privacy, almost best possible privacy, with low latency for a problem that I think is important in terms of privacy. And there's still room to grow, but I think it's showing that we can be on a path towards a much more privacy protecting internet. So I'd like you to think about this picture. Like this is the world we'd like to be in. We have the tools. We just need to figure out how to use them in the right way to get there. And I hope that, okay, this is not to scale, but I think we made a little step. And I'm optimistic, especially talking to students here, that we're gonna be able to do much better in the future. So I think that's where I wanted to finish. I guess the one thought I wanted to leave you with is that I think the barrier to seeing this stuff used in practice very quickly will not be technical. Like right now, you can't build Google search say before this paper, no one knew how to build Google search at scale. But as we get better with cryptography and figuring out how to build these systems, I think the technical barriers are actually not going to be the problem. I think the problem is going to be business incentives, figuring out how to convince companies to actually invest in building this privacy-preserving tech. So I think that's kind of one question to think about maybe 10 or 20 years out, is how can we solve that problem too? So yeah, that's where I wanted to end. Thanks so much.